Okay, so as you guys know, today begins a new 6 weeks period. We are in the final 6 weeks of this semester. So today we're going to start a new topic, which is universal gravitation. So we're going to spend all this week on universal gravitation. Today we're going to focus on the concepts. On Thursday we're going to focus on the mathematics of universal gravitation. And next week we're going to get started on work and energy. So that's the plan for the next few weeks from here on out. All right, so let me go ahead and share my screen so I can show you guys what is currently available in Schoology. Just to kind of explain how we're going to navigate throughout today. Okay. So if you log into Schoology, the 6 weeks folder for the third 6 week has already been posted in Schoology. So when you click on that, and today is December the 1st, so you're going to click on the folder for this week. It is a Tuesday. Okay. And today, this is what we have planned. So I'm going to introduce universal gravitation. And then as a class, we're going to watch this YouTube video. It's about 11 minutes as this guy goes over the details of universal gravitation. And so please be sure that you're paying attention to the video so that whenever I open up the assignment, you can answer the question on the assignment whenever that is opened up as soon as we get done with the lecture for today. Okay, so that's the plan for today, is to talk about the concepts of universal gravitation. Again, when I see you guys next class period, we're going to go over the mathematics of universal gravitation. Today, the main focus is just the concepts. Okay. Now, gravity is a force that we're all are familiar with. It is something that we've already talked about up until this point. Everybody in here knows that right now, as you guys are, sitting in your space, there's a gravitational force between you and the Earth. In other words, the Earth is pulling you toward the center of it. So you're being pulled toward the center of the Earth right now, as we speak. So the Earth is pulling on me, right? And I'm being pulled to the center of the Earth. Okay, so we're already familiar with that force. We talked about the acceleration caused by this force. But on today, I want to get into the more details with this force, and not just only talk about the gravitational force between us and the Earth, but also the gravitational force that acts everywhere throughout the entire universe. So guys, it turns out that every mass in the universe has a gravitational force of attraction between it and some other mass. If it is made of matter and it is an object, there's a gravitational force that exists there between that object and another object. So, for example, right now in my hand, I am holding up two balls. Okay, so everybody see this? I have a red ball here and I have a yellow ball here. Okay. Guys, believe it or not, Isaac Newton tells us that there's a gravitational force of attraction between these two objects right now. So right now, these two objects are being attracted to each other. But some of you guys may be wondering, well, Mr. Taylor, if that's the case, how come I don't see it? How come I don't see that attraction? Well, guys, it turns out that the force of attraction is, the gravitational force of attraction is very, very, very weak. In fact, gravity is the weakest force in nature. So even though these two balls right now are pulling on each other, there are other forces involved. So, for example, obviously I'm holding the two balls. There's also the Earth pulling on the two balls. So there's so many other forces involved, and those forces kind of override or overrule the small force that exists between these two balls. So that's why in our everyday lives we tend to not detect it, because it's such a weak force. Now, guys, if I was in space right now, if I had these two objects and these two balls were in space, and there were no other objects around, there were no other planets, they were just right next to each other, then you guys will slowly see that these balls will be drawn toward each other very slowly because of the gravitational pull between the two objects. Okay? So the force is there, it exists, it's just very, 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 very small. Okay. Guys, this force acts very similar to the attractive force between two magnets. Okay. So all of you guys in here are familiar with magnets. So here I have several neodymium magnets in my hand. Um, I have, some magnetic material here, some screws. So guys, everybody in here knows that um, there's a magnetic force of attraction between a north pole and a south pole on a magnet, right? So these objects are clearly attracting each other. Okay, you can clearly see that. And so, guys, this is very similar to how the gravitational force works. Um, Now, the only difference is, well, one of the differences is between the magnetic force and the gravitational force is that the magnetic force is a lot stronger than gravity, like a lot stronger. And you guys have experienced it in your everyday life that if you take a two magnet and you place them next to each other, you can feel that attractive force. Assuming the North Pole is next to the South Pole. Okay, so just like these objects are being drawn toward each other, these two balls right now are being drawn toward each other. That force is just pretty weak. And guys, that is true between any and all objects in the entire universe. So, for example, imagine that you're in your room right now. Let's say your little sister's right next to you. Because you and your sisters are both objects, there's a force of attraction between you. Y'all are masses. So clearly there's a pull between you all, even though that pull is extremely small, relative to the strength of the pull of how much you are being attracted to the earth. Okay. Now, before I show this video here, there's one more thing I want to say here. I want you guys to know that this force of attraction, this gravitational force, depends very much on the distance between the two objects. So, for instance, you're looking at this red ball and this yellow ball. If the balls are close to each other, the gravitational force is very strong, okay, or relatively strong, I should say. So it's relatively strong as they're close to each other. But if the objects are far apart from each other, the gravitational force is relatively weak. Okay, so everybody got that? So the closer the objects get toward each other, the stronger the gravitational pull between them. And the further they're away, the weaker the gravitational pull. Again, think of two magnets. If you have magnets, guys, everybody in here knows that when the magnets are close to each other, the attractive force feels pretty strong. But when the magnets are far away from each other, the attractive force is really weak. Okay, so just like the magnetic force depends on distance, so the gravitational force also depends on distance. Okay. So I'm going to put on this 11-minute video here. He's going to kind of sum up the concepts I just talked about, and he's going to give you guys some more details. And of course, as soon as we get done with this video, you guys can get started on your assignment. But let me go ahead and go back into Schoology.
Good grammar and spelling are important, but if you want to write essays that inspire...
Did you know that when I moved from there to here, I just disturbed the entire universe? By disturb, I mean a force, which is a push or a pull in physics. So when I moved from there to here, I disturbed everything in the room around me. I've even disturbed you, wherever you are on this earth, and the moon, the sun, the stars, everything. It sounds unbelievable, right? But it's true. Stay tuned because you're going to learn more about this on this video on gravitation. And then we'll finish off with our top 3 exam-oriented questions on this topic. Let's start with the basics. When I drop this ball, why does it fall down? It's because Earth is pulling it down with this invisible force called gravity. In fact, the Earth pulls all the objects. That's how I'm standing on the ground, or you're sitting. We know that the Earth pulls the moon the sun pulls the earth and all the other planets with this invisible force. But the interesting question is, do all bodies pull each other with this invisible force? For example, am I pulling this ball right now? Or are you pulling all the things around you? It may seem strange, but the answer is yes. And this invisible force is called the gravitational force, which we are going to analyze. As we learned, everything in the universe is pulling everything with this gravitational force. What's the requirement? The body should have mass. The gravitational force is always attractive. So for example, these two blocks that I have on the table here are attracting each other with a gravitational force. Let's take a look what this force depends on. Force is directly proportional to the masses. What does this statement mean? So let's say the force between these two blocks is 1 Newton. Now if I double this mass, so I'm going to add another block here. So what's going to be the new force between the blocks? That's right, it's going to get doubled. So the force will be 2 Newton. Now let's say we triple this mass. So here we have 3 times of the original mass. Now what is the new force between the blocks? It's going to be 6 times of the original force. So the force will be 6 Newton. So the gravitational force is directly proportional to the product of the masses. Force is inversely proportional to the square of the distance between the two bodies. What does this mean? So we saw that the force between these two bodies was 6 Newton. Now let's say I double the distance between the two bodies. So what will be the new force now? It's going to be 1/4 of the original force. So that's 1/4 of 6 Newton, which is 1.5 Newton. Now let's get these blocks to their original position. Now let's say I half the distance. So when I bring them in, so what will be the new force now? It's going to be 4 times the original force because it's the square of the distance. So the new force is going to be 24 Newton. And this is called the inverse square law. If we combine the relations, gravitational force is directly proportional to m1, m2 by r square, where m1 is the mass of the first body, m2 is the mass of the second body, and r is the distance of separation between the center of masses of the two bodies. So if the mass or the distance of separation between the two bodies changes, then the force will also change. And that's exactly why I said in the beginning of the video that when I moved from here to here, the distance between me and all the objects inside the universe changes. So the force will naturally change, and that's how I disturb the entire universe when I move from there to here. To convert the proportionality relation into an equation, we need to introduce a constant of proportionality. It has the symbol capital G.
But look, guys, I just want to say this here. This is the equation that we're going to be using on next class period whenever we're going to be actually calculating the gravitational force between any two masses. So just keep that in mind. Now he's right here, he's just introducing it, but this is what we're going to be actually going into more detail with on next class period.
So our equation becomes F equal to G m1 m2 by r square, where G is called the universal gravitational constant. Now what's special about it? G has the same value in the entire universe, no matter which two bodies you're considering. The value of G will be the same. The scientists measured the value of G. It's really, really small. 6.67 into 10 to the power minus 11. Now what are the units of G? Well, there's no need for you to remember it you can easily derive it from the formula we just did. So if you rearrange the formula, we get G equal to F r square by m1 m2. So what will the units of G be? Newton meter square by kg square. Now let's get a feel of the value of G with the help of a simple example. If we take these two books, each having a mass of 1 kg, and let's say they are separated by a distance of 1 meter. So what will be the gravitational force of attraction between these two books? For that, let's use our formula F equal to G m1 m2 by r square. So plugging in the values, we get force as 6.67 into 10 to the power minus 11 Newton. So how much is that? It's going to be 0.000, so we have 10 zeros in there, 667 Newton. So it's a really tiny value. Now, will these two books eventually move towards each other? The answer is no. And it's because this tiny force is overwhelmed by the force of gravity. And of course, there's friction of the table involved.
All right, guys, when he asked will these two books eventually move toward each other, and his answer to the question was no, he's talking about here on Earth. Obviously, they're not going to eventually move toward each other here on Earth because, as he said, there are other forces that are involved here. There's the frictional force between the book and the table. There's also the Earth itself pulling on the books, and all those forces are larger than the magnitude of the forces acting between the two books themselves. Now, if we were in outer space, guys, so if these two books were next to each other in outer space, and there were no other objects around, there were no other planets, then eventually these two books would move toward each other. Of course, of course, the rate of acceleration would be very small, but eventually they would meet up because there's a gravitational force of attraction between these two masses.
In fact, gravitational force is the weakest force in nature. Let's place the concepts we have learned so far on our concept board. Here is a list of the characteristics of the gravitational force. Let's look at each one by one. 1. The force is always attractive. We know that a magnet may attract or repel another magnet, but the gravitational force between two masses is always attractive. For example, if this is my sun and this is my earth, we know that the sun attracts the earth. But did you know that the earth is also attracting the sun with this gravitational force? 2. Gravitational force is force at a distance. So there's no need of any contact. We know that the earth is far away from the sun. Similarly, when you drop a ball, the earth pulls it down with the gravitational force, but there's no contact between the ball and the earth. 3. The two forces are equal and opposite. So let's say, for example, the sun pulls the earth with a force of 1 billion Newton. So what is the force of the earth on the sun? That's right, it's going to be 1 billion Newton. But then the question is, why is the earth only spinning around the sun? It's because of the smaller mass of the earth compared to the sun. 4. The forces are independent of the intervening medium. We know that there's no medium between the sun and the earth. It's just vacuum. But even if we filled it with an ocean, it wouldn't matter.
Guys, vacuum, that's just a fancy word that just means empty space. Anytime you see that word in science, vacuum just means empty space.
The force would be unaffected. 5. Independent of the presence of other bodies. So the force between the sun and the earth is not affected by the moon or the other planets. Number 6. The force acts along the line joining the center of the two bodies. Or to be more precise, the center of masses of the two bodies. 7. It's a long-range force. So as you keep increasing the distance between two bodies, the force keeps decreasing according to the inverse square law. But the force never becomes zero. So all the things in the universe, the sun, the planets, the stars, are attracting you, and you are also attracting them. 8. Weakest force in nature. As we discussed before, gravitational force is the weakest force in nature compared to other forces such as electrostatic, magnetic, and nuclear forces.
Hey guys, what's up? So I am super into this website right now. It's Generation Genius. And they cover all the science standards for...
Let's pin the characteristics of gravitational force on our concept board. I hope the concept of gravitation is crystal clear to you now. As we learnt in this video, everything is pulling everything. Hey, what's happening? Oh, that's not gravitational force. It's my friend tossing these. And do remember to like, comment, and share this video and subscribe to my channel. And do check out my website.
Okay, guys. So before we end this topic, I want to say this here. So in the video, one of the things that he stated is that whenever you're using this equation here to calculate the gravitational force between these two masses, remember one of the things that he said is that when you're looking at the distance between the two objects, you specifically want to look at the distance between the centers of the objects. That's very important because when we talk more about this on next class period, it's important that you guys know that the distance r in this equation stands for the distance between the two objects. And so that's what you need to use whenever you're plugging in values in order to solve for the mathematical force of attraction between these two masses. So, so again, whenever you're finding distance, for example, when you look at this book right here, the center of this book is somewhere around here. And the center of this book is somewhere around here. So the distance between these two centers, however long this point is from this point is what goes into this equation here whenever you're solving for the force of attraction between these two books. Again, I just want to say that because sometimes some students will make the mistake of looking at this distance here and this distance here, and this distance is what they think goes into the equation, like the distance between the ends of the objects. But that's not the case. It's specifically the distance between the centers of the objects. So the distance between this center point here and that center point there. Okay. So hopefully that makes sense. All right, guys. So y'all can go ahead and get started on the assignment. The assignment is actually pretty easy. All you have to do is just tell me one thing that you learned from the video.
Force of gravity.
And that's it. All right, any questions for me? So the assignment is pretty easy today. Now, on next class period, we're going to actually get involved with the mathematics. But I didn't want to do that today. I wanted to just focus on the concepts first. And then we'll be ready to handle the mathematics on this class period. All right, if there are no questions for me, you guys are free to go. Have a good one, everyone.
You too.
All right, bye, Serenity.
Mr. Taylor,
Yes.
when dealing with this situation, so we multiply?
Well, we're going to discuss that more on Thursday. But yeah, so like for example, like let's just say you have two balls, and you want to know the gravitational force between the two balls, and you're going to take this mass, multiply by this mass, and then multiply by the constant g, and divide that by the distance. Like I said, we're going to talk more about that on Thursday. Today I just wanted to focus on the concepts. But yeah, you would. That's what you would do whenever you're calculating the force
Yes,
between
sir.
the objects.
We got a project?
No, you don't have a project. What are you talking about?
I thought you just said that. My
No,
bad.
no, no. There's no project. Not today at least, and not this week.
We good to go?
Yes, sir. You're free to go.